Hello, ladies and gentlemen. Welcome to the portal. Once again, we are back with acids and bases. This is a long chapter. There's a lot of information that you need to know. So be patient. So, all of this was in normal period. It will be if we are using a 1 hour period. This would be period number almost 3.5 because the lesson number 2 is 2.5. So okay guys, do not be discouraged by the length of the videos. The content that is being covered in each video is very crucial, and please do not skip. Watch each and every bit of the content so that you will not be left behind. Okay, so today's lesson is going to focus on the conjugate acid-base pairs, the pH scale and pOH scale, auto-ionization of water, ionization constant of water, which is also the equilibrium constant of water, and dissociation or ionization constant of a base. Okay, the Kb, also equilibrium constant of a base, also ionization constant of the acids, Ka. Okay, so let's start, okay, with conjugate acid base pairs. Okay, okay, so now this part is conjugate acid base pairs. Okay, so now you know reactions of acids and bases because we have learned that from our previous videos. Okay, so now if I say I take one reaction of acid and base, okay, so now if I say I take HCl plus water okay, and then I get what? Hydronium ion plus what? Chloride ions in aqueous solution. So by definition of Lowry-Bronsted, what is an acid? Acid is a proton donor. Okay, so between HCl and water, which one is a strong acid? We know that HCl is a strong acid, right? And this time around, water is what? Is a base. Remember, water can act as either acid or base, okay? Because it is what? It is an ampholyte, which is a substance that can act as either base or what? Or acid, okay? Or it is amphiprotic. It can donate a proton and it can also accept a proton, okay? Now, so now this is an acid, right? When we are starting, this is an acid, and then this is what? This is a base. Agree? So now this is number 1, this is number 1. So the reaction between the acid and a base forms what? Hydronium ion and what? And Cl minus. So if this equation were to go backward like this, if this equation were to be reversible, so what is going to donate a proton between this hydronium and this Cl? So in order for something to donate a proton, it must have a proton. So chloride does not have a proton, so it cannot donate a proton, but it can accept. And what is a proton acceptor? A base. Okay, so I name it base 2. So now this one, if the other one is a base, this one must be an acid. It's acid 2. So now conjugate acid base pairs, what are those? We are simply pairing what was an acid before with what it has formed after donating a proton. Okay, so if you can check this HCl, right, which is the acid one, started as HCl and ended as what? As Cl minus. So this is a pair. Why? Because the ions, the anions of the acid and the charge, they are the same, because the proton is being held by what? By the Cl. So it shows us that, oh, the Cl here had a proton, now no longer had a proton. So this is a pair. So now water, it started by being water. Now it is no longer water, it's what? It's hydronium. Okay, so what was holding, what has accepted the proton is the O from the water molecule. So we can see that, oh, this one has an O like that one. Oh, the difference is that this one, this O, H2O, has accepted the proton to form H3O plus. You see, so this one and that one, they are pairs. And what kind of pairs? We say they are conjugate acid base pairs. Why acid base pairs? Because this acid and this base, they are pairs. So conjugate acid base pairs. So these ones, they are what? This is a pair. Okay, and also this one, this is also a pair. So this is a conjugate acid base pair, this is a conjugate acid base pair. You see, so simple as that. There's no rocket science behind this. So we can do another example whereby we have, let's say we have ethanoic acid plus what? Plus sodium hydroxide. Okay, so if they ask you that identify conjugate acid base pairs. Okay, so now this ethanoic acid, when it reacts with sodium hydroxide, here we have a double arrow. Remember, it is a weak acid and a strong base. So now what are we going to get? We're going to get sodium ethanoate plus what? Water. Okay, so this sodium ethanoate is a what? It's a salt. Okay, so now if they say to you, identify conjugate acid base pairs from this kind of equation, what do you look at? You look at what is an acid and what is a base. So we know that sodium hydroxide is a base. Obviously it's a base. And then this is an acid. Okay, so you can identify one of them if you know that one is a base and then you know the other one is an acid. So uh, now from that we can proceed and say now in here, okay, so on the right hand side, what do we have? We have a CH3COO. So when this it is separated from the Na, this becomes what? An anion. Okay, and water, remember that the water is an ampholyte. It can act as a base and as an acid. So this time around in here it will be what? An acid. It will be an acid, right? And now this sodium ethanol will be our what? Our base. But how will it be our base? It will be our base when it has lost what? When the Na it is separated from the ethanoate. Okay, so now this started as being an acid to form what? To form a, a base. And what was a base? Formed what? An acid. Okay, so if you are being confused by the Na, the NAs, this simply looks like this: CH3COOH plus OH minus forward reverse, giving us CH3COO minus plus water. So this looks like that. It's the same thing, but we have removed the spectator ions, which is the sodium ion. So now you can see that this is an acid, this is a base, and then this it had a proton. Now it no longer has a proton. This it did not have a proton, but now it has gained a proton to form water. So uh, acid, base, base, acid. You see. So now the pairs. How are we going to pair them? So let's use this one at the bottom. Okay. So this one is an acid. It will be paired with what is now our new base, and our the base that we have started with will pair it with our new acid, with our new acid. Okay, so we'll pair it with our new acid. Okay, so if they say identify conjugate acid base pairs, this is what you do. So this is a pair and this is a pair, this is a pair and this is a pair. Okay, so that's all there is to it. There isn't rocket science to it. So what you can do on your own, you can identify okay, let me do this. HSO4 minus plus NH3, okay, giving us what? NH4 plus what? Plus SO4 2 minus. Okay, and here I have HCl. Here I have HCl plus HSO4 minus, giving us what? Giving us H2SO4 plus Cl minus. Okay, so in both reactions 1 and 2, identify conjugate acid base pairs. Okay, Let me give you 1 minute to do it. Okay, are you done? So now, what do? We first identify our acid and our base. Okay, so what is our acid between this and that? We know that ammonia is a base. First things first, identify what you know first. We know that ammonia is a what? Is a base. So ammonia is a base. If ammonia is a base, then this must be an acid, isn't it? So let's put the acid in red. So this must be the acid. Okay. So now, what was first an acid will end up being a base, isn't it? So it will be a base, the red base that has resulted from the red acid. So now, what was a base will now be an acid. So this is an acid. Okay, so if I choose the pairs, this will be a pair. Okay, and another pair, this will be a what? A pair. You see, so simple as that. Just look at this one has a sulfate ion. Also this one is a sulfate ion. So sulfate to sulfate. It was an acid, now it's a what? It's a base. And this ammonia was a base, now is an acid. You see, so even here you can identify which one is an acid between HCl and this one. How do you know which one was an acid? Because this one from reaction 1 it was an acid, but now look what happened. So so now if this is an acid, how do I know that this is an acid? Because from being HCl, it is now Cl minus. So it has donated a proton. So to become what? A base. Okay. So it is what now? Now here we have what? We have a base. This is a base. So now if you look at this base, it has accepted a proton to form what? Sulfuric acid. Okay, so we have now an acid. Okay, so and then now what was an acid will now form a what? A base. Okay, so green to green, orange to orange. So okay, this is a pair. And also this is a pair. You see, conjugate acid base pair, conjugate acid base pair. So you have identified your conjugate acid base pairs. Okay, so let's move forward. I believe you can be able to do this. Oh, and note this, that here the hydrogen sulfate on reaction number 1 it was acting as an acid, and on reaction number 2 it was acting as a base. So what is this? What is the term that is used for this, for such molecules that can act either as acid and as a base? They are what? Ampholytes. So we can see that HSO4 minus is an ampholyte. Okay, so you must know that this is an ampholyte. Okay guys, let's check other bulletins. Okay, okay, where are we? All right. Okay, oh yeah, now here, okay, let's talk about the pH scale and the pOH scale very fast. Okay guys, So let me take a nice white pH scale. Okay, pH scale. So now, what is this pH scale? What is this pH scale? So it is a scale of numbers from 0 to 14 used to express the acidity or alkalinity of a solution. Okay, so so it is a scale of numbers, right, from 0 to 14 used to express the acidity or alkalinity of a solution. By now you know that when pH is less than 7 is acidic, when pH is equals to 7 is neutral, when pH is greater than 7 is alkaline. So now let's draw our nice scale here. Okay, so now if this is 7, then here we have what? We have 0, and then here we have 14. So here this is borderline. On the borderline we are neutral. Okay, we are neutral. And then on the right of the borderline of pH scale we are what? Alkaline. So, or basic. So, and then from the to the left of the borderline is what? It's acidic. Okay, so here we know that pH is what? It's less than 7. Then this side pH is greater than 7. Okay, so we can calculate pH of strong acids and strong bases using formula of pH. Okay, so now here we will calculate pH of pH values of strong acids and strong bases using the formula pH is equals to negative log the concentration of hydronium ion. Okay, so now how do we calculate this new thing, this beautiful thing we say it's pH? Let me highlight it so that it becomes very nice. You see, this is beautiful. We are going to use it as we go further. So our calculations start here. Okay, so now we can calculate pH when we know the concentration of the hydronium ion in the solution whereby we have ionized an acid. Okay, so for example, let's have an example. So if our example says that calculate the pH of a solution that has a hydronium concentration of 0,125 mole per decimeter cube. So now they're telling you to calculate the pH of a solution that has a hydronium concentration of 0,125 mole per decimeter cube. So what do you do? So first things first, okay, you write the beautiful equation. This is the beautiful equation. pH is equal to negative log of concentration of what? Of the hydronium. Okay, so you write it as it is. Do not omit anything here. So negative log. This log, which log is this? Is the base 10 log. On your calculator, if you are using the Casio FX82, I'm using the old model. So the log I'm talking about, the base 10 log that I'm talking about, it is on the same row as the ln function. It is written in for you because you don't know what is a ln or a natural log. You know it as in. Yeah, it is next to in, so it's just written log. Okay, so this is the log that you're going to use. So and then now inside the log you will substitute the 0,125. Okay, and then now you proceed to press your calculator. Okay, so I'm pressing mine. Unfortunately I cannot share it on the screen. So negative log of 0,125, and then you close the brackets. Okay, and then equal sign. So I'm getting how much? I'm getting 0,90. So, and notice that pH, it is a unitless value, so it does not have units. So as long as we know the value of pH, we are fine. Okay, so now because we know the value of pH, now it's 0,9. So if we go back to the pH scale, the pH scale says that it starts from 0 to 7. Okay, so the borderline or the middle line being the neutral line, which is 7. So anything less than 7 is acidic and anything greater than 7 is basic. So according to our calculation, the pH of a solution that has a hydronium concentration of 0,125, now is it acidic or basic? We look at the value of the pH. Oh, it's less than 7. So this pH is less than 7, isn't it? So therefore it is what? It is acidic. Okay, it is acidic. So but you are not asked that question. They just said calculate the concentration, calculate the pH of a solution that has that concentration of a hydronium ion. So you will end here on 0,9. Okay, so now when they mark this question, this is what they do. 1 for the formula, for the correct formula, 1 for correct substitution, 1 for correct answer. Okay, So now this, you would only write this when they have asked, is this solution acidic or basic? And then this is what you would write. And then if they ask, why are you saying this solution is acidic? You say because pH is less than 7. Okay? Now, so, okay, example 2. Example 2. Okay? So, now, calculate the pH of hydrochloric, calculate the pH of a hydrochloric acid solution. If the concentration of hydrochloric of HCl is 0,0 is 0,123. Let me say 135. Okay. Calculate the pH of a solution, or calculate the pH of hydrochloric acid solution if the concentration of HCl is 0,135. Okay, mole per decimeter cubed. So what do you do? Okay, so now I'm giving you another statement now. Assume HCl HCl ionized completely. Let me say ionized. Assume HCl ionized completely, or assume HCl is ionized completely. Yeah. So now, how are you going to answer that question? So first things first, they are telling you about the concentration of HCl. So what they are telling you, they're giving you the analytical concentration of hydrochloric acid. They say it's equal to 0,135 mole per decimeter cube. They have not told you anything about the concentration of the hydronium ion. How can we calculate the pH? We need the concentration of what? Of the hydronium ion, isn't it? So because we need concentration of hydronium ion, and they did not give us concentration of hydronium ion, so what do we do? So this HCl in aqueous solution, what does it form? HCl plus water, right? It gives us what? It gives us the hydronium plus Cl minus. So now it is balanced, as you can see. So now we're going to check the stoichiometry between the HCl and the hydronium. Okay, going to check the HCl and the hydronium. So the stoichiometry, the moles, for every 1 mole of HCl that ionizes, 1 mole of hydronium is what? Is formed. Okay, 1 mole of hydronium ion is formed. So now I can say concentration of hydronium. I have to calculate concentration of hydronium first. Concentration of hydronium is equals to the analytical concentration of HCl, which is 0,135. Because this is 1 is to 1, so multiplied by 1. You see, multiplied by 1. Because for every 1 mole of HCl that ionizes, 1 mole is formed. So of hydronium is formed. So 0,135 times 1. what do I have? I have 0,135 mole per decimeter cubed of what? Of hydronium ion. Okay, so now I can take this information and substitute it into my beautiful formula. Now I am going to substitute it with pride, because now I know that what I'm substituting, it is what? The concentration of what? Of the hydronium ion, rather than the concentration of what? Of the HCl itself. So now when I press my expensive Casio calculator, which you guys also have, now what do I get? I get a pH of 0,887. Okay, 0,87. Okay, 0,87. Okay, so now here the question said calculate the pH of hydrochloric acid solution if the concentration of HCl is what? 0,135 blah 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 blah. Okay, so now let's take example 2. So example 3, right? So example 3, they say now calculate calculate the pH, calculate the pH of a solution of of sulfuric acid if the concentration of H2SO4 is 0,135, okay, mole per decimeter cubed. So calculate the pH of a solution of H2SO4 if the concentration of H2SO4 is 0,135. So now note how this is very tempting. It is very tempting that you can just directly say pH is equals to negative log of concentration of hydronium, and you substitute that 0,135. It's tempting, but please don't do it. Okay, so now the minute I talk about solution of sulfuric acid, it means that the sulfuric acid is in what? In aqueous solution, is in water. Okay, so when it's in water, sulfuric acid in water, what does it form? It forms hydronium ions. Okay, so now sulfuric acid is a diprotic acid, remember. So sulfuric acid in aqueous solution, right? Sulfuric acid in aqueous solution forms what? Forms 2 hydronium ions plus what? Plus sulfate, ions. So now we can tell that every 1 mole of sulfuric acid that ionizes in water, 2 moles of the hydronium ion will be formed, isn't it? So now, even with concentration, it works like that. So for every one for every concentration of for every 1 mole per dm cubed concentration of sal sulfuric acid, okay, so for every one concentration of sulfuric acid, 2 two hydronium ions will be formed. So for every 1 mole per dm cubed of sulfuric acid that ionizes, 2 mole per dm cubed of hydronium will be formed. Okay, so now you can see that the moles and the concentration, they work the same in terms of stoichiometry. Okay, so now, because here I was just showing you what is needed, okay, so now let's go on and calculate. So now we are given what the analytical concentration of what H2SO4, which is 0,135 mole per dm cubed. Okay, so now we want what? We have to get concentration of the hydronium. So the concentration of the hydronium, because for every 1 mole per dm cubed of H2SO4, there's 2 mole per dm cubed of hydronium. So we are going to have so we'll have 2 times what? Times that analytical concentration. 2 times 0,135. Okay, so now what are we going to get? We are going to get 2 times 0.35, which is 0,27 mole per decimeter cube. Okay, so we can take this 0,27 now and put it in the pH equation. Negative log of hydronium, you write it as it is. Okay, so negative log of 0,27. Okay, so what do you get? You get 0,56. Okay, so which is still which is acidic, so it's less than what? It's less than 7. So this is how you deal with a diprotic acid. You have to take into account the what? The stoichiometry. Okay, so some of you might not understand what I have done here. Okay, so from grade 11, what I have done is this: 1:2, right? Okay, so the number of moles of the acid, the concentration of the hydronium. I didn't have the concentration of hydronium here, so I put X. And then now here I have what? Concentration, the analytical concentration of sulfuric acid, which is 0,135. Okay, so now if I cross multiply, I will have X times 1 giving me 2 times 0,135. You see how why I multiplied this 0,135 by 2. Okay, this is the reason. Okay, guys, I am done with pH. Okay, so we also have what we have POH scale, also 7, we have 14. Okay, here is 0. This is what POH. It also a scale of numbers from 0 to 14 to express the acidity or alkalinity of a solution. So here, 7 is what is borderline, is neutral, and then because this is POH, it's no longer pH. So in here is what is acidic, then here is what alkaline. Okay, so now if pOH is less than 7, it means what? Alkaline, right? And if pOH is greater than 7, it means what? Acidic, pOH. And then now this also works like a pH. So but here you use the formula of pOH. So pOH is equals to minus log of what? Of concentration of hydroxide ion. Concentration of hydroxide ion. So now, for example, you are given they tell you calculate the sorry, calculate the pOH of a solution of NaOH, right? Of NaOH, and then assume that the NaOH dissociate completely. Okay, assume that the NaOH dissociate completely. Okay, so what are you going to do now? So we know that NaOH in water, when it dissociates, it gives us Na plus OH minus. So the stoichiometry between the NaOH and OH minus is 1:1. Agree? So now we know that okay, so for the concentration of yeah, I did not give you the concentration. Okay, so calculate the pOH of a solution of sodium hydroxide. Assume that okay, so if the concentration of sodium hydroxide is what 0,53 mole per decimeter cube. Okay, so now this CNaOH is just the concentration of sodium hydroxide. It's not the concentration of hydroxide ion itself. So this concentration, as I've been saying, it is called the analytical concentration. So now here we know that between the sodium hydroxide and OH minus we have 1:1 stoichiometry, right? So for one, this I have what? I have one concentration of what? Of OH minus. You see? So now I can calculate my OH minus concentration using what I've been given. So concentration of OH minus, this is 1:1. So it will just be what? It will just be 0 comma what 53 multiplied by 1. Okay, so it's what 0 comma 53 mole per decimeter cube. Okay guys, so now I can be confident that, oh, I can calculate POH. I can calculate POH. Okay, so now minus log of concentration of hydroxide ion. So I'm going to get negative log of what? 0 0.53. And when I press my expensive calculator, what do I get? I get 0 0.53. Negative log of 0 0.53 is what? 0 0.28. 0 0.28. So now what does this value tell us? It tells us that the solution is what? Is basic. Why? Because the pOH is less than 7. So uh, so if they ask you, is the solution acidic or basic, you're gonna say solution is basic, isn't it? Why is it basic? Because pOH is less than 7. Tango. So you know now how to calculate pH from given concentration. Okay, so now let's up the stakes. Okay, so what if now they give you a concentration, they give you pH, and then they want what? They want a concentration. So and then they say, example, okay, now a solution has a pH of 7,8, right? Calculate the concentration of the hydronium ion. Calculate the concentration of the hydronium ion. What do? We know that we have this beautiful equation, negative log of what? Of hydronium ion. So what are we given? We are given a pH of 7, 8. We just put it there. Is equals to negative log of what? Of hydronium ion. Okay, so now how are we going to solve this concentration of hydronium ion? So what we do is that we must make this hydronium ion subject of the formula. So remember that this is base 10 log. So in order for us to remove a base 10 log, we must introduce a base 10, and making this log of hydronium an exponent. Okay, so now if I introduce a base 10 both sides, wait, before I introduce base 10, let me divide by negative both sides. If I divide both sides by negative, I have a negative 7.8 this side, then the other side I have log of concentration of hydronium. So if I introduce base 10 both sides, I'm going to have negative 10 exponent negative 7.8 is equals to 10 log of concentration of hydronium. But this and this, they are what? They are inverses. So they will cancel out, and then we will have what is inside this log. So I will have 10 to the power minus 7.8 is equals to concentration of what? Of hydronium. And then now I can proceed and press my calculator. So 10 to exponent negative 7.8. How much am I getting? I'm getting that the concentration of the hydronium is equal to 1.58 times 10 to the power negative 8 mole per decimeter cube. Guys, please, every time when you write your answer, check if the answer that you are writing requires units, okay, and write the correct units. If you don't write the correct units, you will be penalized. So this question is worth what? 3 marks. So 1 mark here, 1 mark for substituting, and 1 mark here. So now here, for doing this beautiful work, you're not gonna get any marks. So to solve that for you, I'm going to give you a formula that you will readily use to calculate concentration of hydronium ion. You just say concentration of hydronium ion is 10 exponent negative pH, and then you just substitute this. So if we were given this, if we knew this formula, we were going to just use it and substitute it. So I was going to do this 10 exponent negative 7.8 blah blah blah. I get the answer 1.58 times 10 to the power negative 8 mole per decimeter cube. See how short this is. 1 2 3. You see, so this is short. You can use this instead of trying to make hydronium subject of the formula. So here I have used the same method that I've used, but some of you will get confused and end up making unnecessary mistakes. So you know, when they are asking for concentration, you go straight to this, okay? Also for pOH, if they say also another example, calculate calculate the concentration of hydroxide ion if a solution, or let me say in a solution with a pH pOH with a pOH of 3.5. okay, so what did they give you? They've given you pOH, the one concentration of hydroxide ion. So what do you do? Similarly to that one, remember pOH is equal to negative log of hydroxide. So the same mathematics applies even here. So here I have this negative 10 times 10 exponent negative pOH. So now what will I do? Here I will substitute. I will say 10 exponent minus 3.5, and then I punch my expensive calculator. I get minus 3. I get 3.16 times 10 exponent negative 4 mole per decimeter cube. Guys, concentration is measured in moles per decimeter cube. Okay, so this is how you calculate pOH. This is how you calculate concentration of hydroxide ion from given pOH. Okay, so, and now we have covered the pH scale and the pOH scale. So now let's conclude this video, and you can go and practice more. So the next video will talk about uh, what's that? We'll talk about equilibrium constant of water, okay, and equilibrium constant of acid, and what? And base. Okay, guys. I love you so much. Thank you for tuning in. I wish you the best. You know, this is one of the best channels, if not the best. Please don't forget to like, share, and subscribe. Thank you.